Hello, everybody. Welcome to the Cortus webinar. The topic today doesn't need any introduction, but I will introduce the presenters. My name is Dan Janusis. I'm going to be your moderator today, and joining me is Tim Davis, who's the president of Aspen Logic. Aspen Logic is a logic design and verification consultancy, and they're experts in the RTL design process and assist people in ASIC and FPGA design. Also joining me is Roddy Urquhart, who's the vice president at Cortus. Cortus is an IP provider based in France. It provides processor IP and peripheral IP to people building ASICs and SoCs. Before we get started, let me just ask you, if you have a question, feel free to either use the chat window or the Q&A window. Send us a message. We'll collate all those and answer them at the end of the webinar. So although the title doesn't need any introduction, the agenda does. Today we're going to be talking about the advantages of why you should build your own hardware. The essential question for the IoT is, as you're building your things, are you going to buy off-the-shelf components, write some software, and make that a product, or are you going to build your own silicon? If you are going to build your own silicon, how are you going to do that? What are the options for building prototypes, production ASIC manufacturing? We're going to talk about the design process, the RTL and analog mixed signal flows that are required, how much experience is generally required so you can get an understanding of what it takes to build your own hardware. And lastly, we're going to talk about what intellectual property is available to assist you in integrating your ASIC as opposed to designing everything from the ground up. So why is hardware important in the IoT? Well, this is a picture from our good friends at ThingWorx, their PTC business. And what they're showing you here is quite a bit of software. When people talk about the IoT, most of people say the value is in the software. It's in the analytics that you can run. It's the integration of your factory into CRM and ERP systems. It's using the cloud services, lots and lots of software. But the reality is none of that software is important without the hardware. The hardware is what connects that software to the real world. It's the eyes, the ears, the taste, the smell of everything that's happening that allows that software to actually be of value. And with the IoT, what people have realized now is that we can't simply use the dumb kinds of sensors that we've had all our, in the legacy, just collect all that information, ship it back up to the cloud, and let all the software work on it. That's just not a tenable solution. And that's why people are pushing for what's called edge analytics now. And that basically is saying, put some intelligence out into the hardware, do some processing at the edge points, and then send back either metadata or some of the decisions you've made. But hardware is important for IoT because it's essential that that data be accurate, be secure, be maintained, and with most of IoT, there's either things are running on batteries or they have large thermal issues. IoT, by essence, you're going to have things sitting on a car seat in the middle of the desert, or they're going to be on a mountaintop at a ski resort. They're going to have thermal issues. They're going to have battery issues if we're wearing devices, if we're carrying mobile devices. So power is a huge concern here. It's not just what's the cost and what's the available. If you want your product to stand out, if you want your thing to rise in this IoT revolution, you're going to want it to stand out. If you think about what happened with cell phones, what happened with the internet when it first came out, there were a lot of new companies that quickly became very, very valuable and successful. And in each one of those, they made smartphones, they made tablets, they made communications, they made sensors, they made networking equipment that all made their software stand out. So what are the advantages of an ASIC over just buying off-the-shelf hardware? Well, the first thing is it's not about performance. The IoT and things really changes the paradigm for how we've thought about building silicon over the years. In the past, it's been a race to the highest speed. If you remember back in the days when PCs came out, or when workstations came out, it was always who was at 10 MIPS, 100 MIPS, who was running the fastest. And indeed, today, if you look at some of the high-end things, they're running quad-core chips at 1.2 gigahertz for smartphones. But the essence for the Internet of Things is to balance that. It's to be efficiency. It's to get enough performance at the minimal possible power consumption. So you have this trade-off of dialing up all the speed you can and getting to the point then where you can cut back and minimize power. Second big advantage is by going to integration, you can get all of your devices into a smaller package. Form factor right now is going to be huge. These sensors are going into the industry, they're going in automobiles, they're going into satellites, they're going on our bodies. We don't want to be lugging around the big bricks of cell phones like we did in the early 90s. We want a small, sleek, ergonomic kind of device that'll fit easily into our things that we're building. And with that integration, of course, comes better reliability. The last thing we want to do, I've heard people talk about Google Glasses, where the reliability and the battery life has been unacceptable. Serviceability, as we get in further into the industrial IoT, is going to be very, very important. We're going to have to make sure that we can maintain the usability of all these things as they go out. And, of course, security is going to be a huge issue. In fact, most people, when they talk about IoT, they say security is not only the issue, it's the most important issue. And I like to talk about people that think that they're going to go buy off-the-shelf processors and then load some software around. That's like a moat around a castle. And even the Monty Python folks figured out how to catapult cows into the castles over the moat. Software security is minimal. Hardware security is the most secure implementation. And when you build your own hardware, you get to build in that security. And as our friend Alan Kay said way back in the early 80s, if you're really serious about your software, if IoT is really all about software, you should be making your own hardware. But to be fair, let's look at the balance and the trade-offs of each approach. As I've said, on the ASIC side, if we're building our own hardware, we can dial in speed and power and size and reliability, lower costs, and all the security we want. But nobody likes to move. And if you've had software you've written on a processor that you've bought from an off-the-shelf provider like TI or Atmel or Microchip, there's some essence of the value of not having to move. There's no down payment. I live about a mile from SparkFun Electronics. I can ride my bike over there and pick up a Raspberry Pi board tomorrow, a couple sensors. They have a nice demo in their lobby of a Blender Defender that one of their makers had built. The cat would jump up on the kitchen counter when they were gone. So quick little Raspberry Pi board, a sensor hooks into a power supply for the blender. Cat jumps on the counter, blender goes off, cat disappears. It's a beautiful thing. You can put that together, but that's a hobby. That's not what we're talking about. We're talking about real applications of technology to solve real solutions like in the industrial IoT. And there's almost zero tools cost. You probably already have tools for making printed circuit boards, for doing embedded software development, but you don't have to buy any boards if you buy off-the-shelf parts. In fact, people like Microchip are now offering cloud-based tools for free. Of course, security-wise, not a lot of people want to put their design data up in the cloud, but it's almost zero type of cost. But what that gets you is almost zero differentiation. You're using the same processor, the same tools, the same components as everybody else. You're going to have about the same product as everybody else, and there's just not enough software differentiation to help you stand out. I was at the Designer of Things conference in November, and I live in Colorado, so I'm, of course, always interested in skiing. And there was a company there debuting their new thing. They had put 3 sensors into each ski boot. They had equipped it with a processor, some Wi-Fi, a bunch of technology, and they were able to sit at the base, and your coach is able to see how parallel your boots are, what angle they are on cuts. These are for high-performance skiers to give them that ergonomic feedback of what it feels like in my boots to how to improve my performance. And I was impressed, and I looked, and it's about a cigarette pack hanging off the back of each boot. And I asked the vendor, well, what's that for? And he said, well, we bought off-the-shelf processors. We bought some lithium batteries. We bought a bunch of stuff. We put it on a board, and we hung it off the back of the boot. It's not so bad. And I said, well, why wouldn't you build your own hardware? Why would you if you built an ASIC, you could slip it inside the boot. It wouldn't even be noticeable. It would be underneath the cushions. It'd draw a lot less power. It would be a lot more secure and a lot more reliable. Nobody behind you is going to use their ski pole to knock your cigarette pack off your back of your boot. And he said, oh, well, we called the people and found out what's it going to take to build an ASIC. And this is the vendor telling me, he said, when we heard it's going to take $25 million just for a mass cost, we said, yeah, right, that's not going to work. And 6 months to get prototypes? Are you kidding me? And who in the world wants to pay $2 million a year to these tool vendors just to design a piece of silicon? And we don't have 20 years of designing experience, so that's why we use off-the-shelf components. Well, let me give you some good news. All of those things that he was talking about don't apply to the IoT. What he's talking about, and when you call an EDA sales guy or you call a foundry, they're going to want to sell you their latest, greatest tools. They're going to want to sell you their latest, greatest silicon because that's what salespeople do. But the big change in IoT is we're not building bleeding-edge ASICs. You're not running at 2+ gigahertz. You're not building a billion gates. The good news is that the mainstream ASICs that are perfect for the IoT are mature. They've come way down in pricing because all the R&D has been paid off. Literally now you have time and materials to make silicon, and there's plenty of horsepower. These processes can run up to 500 megahertz at an incredible power efficiency. They don't leak nearly as much as the advanced nodes do. More importantly for IoT, you can put your analog on board. IoT is all about sensors, wireless radios. Basically, there's a lot of analog. You can put that on your mixed signal on your die. And it's low risk. This stuff has been around for many, many years. There's plenty of providers, as we're going to show you, and get all your memory on board. So don't believe those myths about ASIC design. Those are for the leading, bleeding edge guys. One helpful rule to keep in mind is called the ASIC ROI of 50. And if you look at your bill of materials and you can identify $50 worth of parts on your bill of materials that you can integrate into an ASIC, and you're going to produce 50,000 units or more, then you're going to have a positive return on your investment in that ASIC. So this is a real easy back-of-the-napkin kind of thing to do while you're sitting around thinking about should we be building our hardware or not. Use that rule of 50. It's been proven years and years and years and still holds true today. So when we talk about processes, there's everything from leading bleeding edge of measured in nanometers all the way up into micrometers. And when you see the design starts, you can start to get a feel for what we're talking about here. When TSMC comes out, they talk about their process available today, everything from 0.18 micron, which to many bleeding edge people would be like riding a fat tire bicycle in an Olympic event. That just seems to be so 1990s. But it all goes down all the way down to the 14 nanometers. But when you want to build an IoT ASIC, you're going to want that embedded flash memory on board. You're going to want analog. And so it turns out that the majority of these processes, including mixed signal, actually run all the way down to 40 nanometers. And in most of the design starts for this year, 80% are going to be in processes that are appropriate. So there's safety in numbers. These processes are out there. These fabs are reliable, they're secure. They've been in production for many years. They're predictable. These trains have been running. You can rely on them. And how do you get these parts through these foundries? If you've never done this before, there's a service called MPW. And MPW is called a multi-project wafer. What they're talking about is a communal die. That's the way I say. You can have some research people that are doing some small dies, and the vendor will assemble all those onto one die, put those all on a wafer for you, give you a nice updated schedule of weekly trains that are leaving, wafers that are going into the fab at each different process node, so you can decide where you're going to get on, where you're going to ship. But this is an extremely low-cost, low-risk way of getting your prototypes. Some vendors like eSilicon have this on their website. You can go in and dial in exactly which vendor you want. They have 7 vendors that you can pick from. All are going to have different pricing, different processes, different schedules. But that's the service that's provided to you. You don't have to be experts in this. You deal with an eSilicon. You deal with a MOSIS or a Europractice. They'll take good care of you. In fact, you can even go online, eSilicon website here, and they have an Explorer tool, and they'll tell you right up front about what the minimum investment. You're going to spend about $5,000. You're going to spend about 2 months in 65 nanometers, about 1 month in anything larger than that. you're going to have 7 foundries to compete with on availability and pricing, on which process. All of these services are available online to very, very easy to just to get the data you need to make a good decision whether you want to use this or not. But essentially, most of the costs and most of the risks are greatly reduced when you use MPWs, and this is a very common way for people to get into ASIC design in the Internet of Things. Once you go into production, there's a whole series of foundries out there. TSI is in Sacramento. This used to be the HP foundry. You have foundries in Taiwan. You have foundries in China. You have foundries in Europe. All of these are available for you. They're all in full production mode. And then you also have other availability for, you don't have to deal with the sales guy. Go online, fill out the form. 2 days later, you get a quote. Here's how much it's going to cost. Here's your availability, when you're going to receive it. Here's the packages that are available. All that's available. Out of Israel, there's a nice website called AnySilicon. Lots of resources available on that website. You can find out which vendors tend to favor which processes, which vendors have more analog components to use, etc. But all these resources are online and available for you. And from ARM, we have a kind of a pricing model here, just to show you in 180 nanometer design, you're going to spend about $2,000, okay? And you're going to get 45, 50 samples. When I say samples, these aren't going to be burned in production devices. These are your prototypes. But the point being is it's not a big expense. It's not a big lag time to get these samples back. And once you go into production, it only costs you about $16,000 for the masks to generate this at a fixed cost. Now, what we're showing here is that the cost is going to be the same for every die. What's going to change is your price. As you get up in volume, you're going to see. But $50 is going to represent kind of the highest price that you're going to have in that. As you go up into the fabs, of course, the mask costs are going to increase. You might see about double is a good number as you jump these process nodes. So as we said, up around 65 nanometers, you're talking about $4,000 or $5,000 NRE. None of this is going to break your bank. None of this is going to send you running off to an investor looking for a new round so you can build a new piece of die. And in fact, most of the time, this is about what people spend on beer in their engineering labs anymore. So tell your engineers, there's no beer next month. We're buying prototypes. Bring your own. As we get into the design flow, you're going to find that on the digital side, if you've never done ASIC design, it's completely text-based. Back in 1988, there was a transition. Cadence was leading the way. In fact, at one of the trade shows, they handed out crayons and coloring books to people and T-shirts that said, "Real engineers write code." And they're talking about schematic-based design is over. If you're a hardware engineer, get over it. You're going to write code to represent the hardware. It's been shown for 20, 25 years to be highly productive. Every piece of advanced silicon today is written in an HDL, a hardware description language. Sometimes we call it an RTL for register transfer language. But essentially, it is a way of representing in code how the hardware is supposed to function. And then that code is simulated in a simulator, and you're going to get waveforms. You're going to be able to, probe different nodes. You're going to be able to display results and registers, everything you need to do to functionally verify your design. Then you're going to synthesize that. You're going to take that text, the tool, you're going to give it some constraints, tell it how fast you want it, how small you want it. You're going to give it instructions on how to build certain things like state machines, whether you want them in parallel case machines or one-hot encoding, or whatever you're doing for your decoders. But essentially, it's going to create your gate level, your flip-flops, your AND gates, your NOR gates. We're getting a gate-level representation that we're going to ship to your vendor who's building your silicon, and they're going to place and route that. And all these little lines are all the gates that you've presented in your RTL, wired together in what's called channels, and they're going to send that back to you, and you're going to then simulate it with the actual timing of the wires and the gate delays. So as you go progressing through this, you're going to do a series of verifications. But the point being, they're not difficult to learn. People that pick up RTL design, Tim's going to talk to this a little bit later, this is weeks of kinds of startup pain. It's not years and years. Now on the analog side, things are a little different. Analog is very much black magic to me. I'm a digital guy, tried and true. To me, I would never design an analog component. I would assemble them as on a breadboard, and that's what the tools look like. You have libraries and components, whether they be DDA converters or PLLs or whatever the analog function. You're going to wire them together. You're going to simulate that. It's going to be very much like looking at an oscilloscope, and you're going to do the physical design. You're going to put them where they need to be, because guarding and the analog effects of analog design are hugely important. So you're going to do all that. Most people are going to use analog IP. They're going to buy libraries of these components and put them together. They're going to get it right, and then they're going to put the two together. And you're going to do analog and digital mixed signal analysis. And this is where everything comes together. You're going to verify that the digital to analog boundary is done right, that everything resets correctly, everything interacts correctly across clock boundaries. All of that's your final validation of your design. Next, you're going to send all that information, and your vendor is going to put it together. He's going to do all his physical verifications. They do design rule checking. They do electrical rule checking to make sure you have enough power and ground pins. All of those things are going to be taken care of for you, and they're going to come back and finish the design. You're going to sign off on it, and away we go. The thing to remember here is that these flows are proven. They're easy to adopt. They've been around a long, long time. They're not very buggy, and the amount of FAQs, tutorials, online learning, training courses that are available make this very easy to adopt. But what are they going to cost? Well, again, we have the same thing in the tools issue. We have tools from the top EDA vendors that run millions of dollars a year per engineer. They have to do the advanced, to get something to run at 2 gigahertz is an incredible amount of tools required. But we're not doing that. And there's a whole bunch of companies out there that provide tools to people building things that are appropriate for the IoT. Now, true, just like the auto industry, every other industry, there's consolidation. Mentor has bought Oasis, they bought Tanner, they bought Model Sim, Cadence has bought Get the Chip. But they're still operating independently. You can still go out and buy directly from Tanner, just like you would buy from, a Volvo dealer that's part of the Ford Motor Company at this point. What are the criteria you should look for? Well, again, cost is going to be based on functionality. These vendors try and reduce their cost by saying, I'm going to limit the number of gates you can simulate in the simulator, or I'm going to limit the performance that I can provide you on this so that I can give you a lower price tool, because you're doing lower price, lower capability designs. You have to think, am I willing when I do the simulator to go get a cup of coffee? Is this something I want to kick off and go to lunch, come back and look at? And when I get to the end, it's the whole design at the top level. Am I willing to launch it on 20 designs, simulating on 20 servers, and come back in the morning and see what's going on? These are the kinds of things. Iteration in digital and analog design is important, so you're going to want to run 6 or 7 or 8 kinds of iterations a day until you get the design mostly stable. You're going to like buying a car. What's the dashboard feel like? When you jump in, you're used to having the radio here, you're used to having the light switch there. It's the same thing. Some user interface is going to be unique to the vendor. Does it feel good to you? Things where they're supposed to be. We all know when you want to save something, you go to the file menu and you say save as. Is that there? Is it something odd? And how does it feel? Is this going to be productive for me? My advice to you is, if at first it doesn't feel intuitive and efficient to you, it's probably not, and you should probably think about that quite a bit. Mixed signal design is going to be very important to these tools. If you're talking to a tool from, say, Anner that has analog, and you're wondering, will that simulate with a digital simulation from Aldec, ask the questions. You might have something running on an FPGA board, and you want to plug it into the digital simulator. Find out about all those interfaces. And all the libraries are going to come from the people building your silicon. So when you are looking at the tools, trying to make a decision which tools you're going to buy, go to your vendor where you're going to buy your silicon from and say, hey, do you support the Oasis synthesis tool? Do you support Model Sim simulation? Those probably are answered on their website, but certainly a call to them to be happy to help you with that. And since you're probably new to this, support's going to be a big deal. The smaller vendors are going to turn on a dime to support you. If a vendor has 50 customers, they're going to treat those 50 customers as 50 of their best customers on the planet. If they've got 50 million, Well, you're going to have a call center. You're going to call them. And you're going to fill out a ticket. And someday down the road, in a couple of days, a local FAE is going to call saying, hey, I got a ticket. You having a problem? Think about that kind of support as you get going. Look at their web content. Do they have FAQs on there? Does it make sense? And when you get to costing these tools, it used to be an EDA that you bought the software, it was yours, and then you paid a maintenance fee on it to keep it updated and current. All that went away several years ago. And now it's what's called time-based licenses. And some vendors actually will sell you like a 9-month license for their tools. They're trying to give you an affordable solution that meets your project needs. If your thing is going to be built in 4 months, why would you buy a 3-year license to a simulator? I always recommend to people, because I have been an EDA salesman, everything is possible. Don't feel like the price on the window of the car is what you're likely to pay. Talk to the EDA sales guy. He wants your business. Tell him what you can afford, how long your project's going to run. Let him be your advocate to go back to his boss and get you a good deal, because good deals are available. I've given them and I've bought them. I've been on both sides of that table. But in essence, true, the bleeding edge ASICs are going to cost you $1 million a year. But for somebody building an IoT ASIC in 130 nanometers, 90, 65, even down to 40, you shouldn't think of more than $100,000. In fact, $50,000 is where I would budget. You're going to have plenty of tools available at that cost. And again, be a buyer, negotiate, pit the vendors against each other, get a good deal because it's available. And a timely article from last week out of Electronics Weekly. Doesn't have to be a rich man's game. Again, the mature processes are going to make your tool cost drop significantly, because you're not going to need a lot of the features you need to do bleeding edge ASICs. So don't overbuy your tools. If you're building a treehouse, you don't need a CNC machine. You need a saw and some drills and some screwdrivers and pliers. So with that, I'm going to turn it over now to Tim Davis. As I said, Tim is the president of Aspen Logic. He's going to talk about FPGA development boards and their role here in the IoT ASIC design process. So, Tim, it's all yours.
Thanks a lot, Dan. Well, few designs today survive exposure to the real world, right? You need a way to get your design produced and out in front of customers and investors and whatnot. And FPGA development boards are an ideal way to do that. And what they allow you is a chance to get early experience with the system level integration. You get your processor hooked up to your memory, to your caches. You get software running to talk to your comms, be it Wi-Fi, NFC, etc., and maybe some simple user interface elements. IoT devices may not have a lot. Maybe there's a few switches or a dial or a small display, but an FPGA development board is going to allow you to start testing those elements right away. But also, you're going to be able to follow some agile development processes. You're going to be able to start your software development early on real hardware, okay? And you may find yourself needing the ability to pivot quickly to some new capability. Marketing guy comes in and says, hey, we talked to a customer who needs this feature. Can we do it? Well, you can quickly produce a change in your RTL, plug it into the FPGA development board, and maybe even show it to that customer. Embedded software debug and testing can be done very easily inside an FPGA development platform. There's all kinds of debuggers available out there that work by JTAG. It's going to be a lot easier to do on actual hardware than it is inside a simulator, for instance. And I think most importantly, the user interface is going to be, you're going to be able to evaluate that with your FPGA prototype. That's very hard to do in any kind of a simulation environment. You're also going to be able to test compliance of your standards to real devices. I've worked on designs where you simulate and simulate and simulate, and it all looks great, and you plug it into the actual devices and nothing happens. You want to find that kind of stuff out early if possible. One of the other advantages that the FPGA prototype gives you is you're going to be synthesizing your design down into gates for the FPGA, and you're going to be able to know exactly how many logic cells are used in that FPGA implementation and translate that into a pretty accurate number of ASIC gates in a given foundry and get a very good estimate for the cost of your ASIC early on. And I don't think I can emphasize this point enough. With an actual physical prototype, you're going to be able to go to potential investors and initial customer projects with, some real hardware, something that they can get confidence that your design is actually functioning and is not some pipe dream on the back of a napkin. Okay, so you want to build an FPGA prototype. There's a number of things that you need to take into consideration while you're doing it. The first thing is I would definitely focus on doing an ASIC design and not an FPGA design. There's subtle differences in kind of the styles and the way you write things, but you're ultimately going to produce an IoT ASIC, not an FPGA design. And there's some references on the web in particular that you can work on. I would go to Sunburst or Sutherland. Those are both places that are excellent results-oriented, experiential kind of websites that are going to teach you about Verilog. You're also going to be able to learn something about the synthesizable constructs that you'll need inside your design at any one of these training course kind of places. Some other things that you'd like to try and do while you're doing this design, they're going to come up in some of those websites. I strongly encourage you to take any kind of ASIC vendor cells that you're going to have in your design and segregate those in their own wrappers, so that you can easily switch back and forth between the FPGA code and the ASIC specific code. I tend to put those wrappers inside the I/O block where it's easy to find them and easy to manage them. You're going to want to put synchronizers in particular off in the I/O ring. Everything that comes into the ASIC needs to be synchronized, and there's going to be special vendor cells for that purpose. I'd also recommend registering all the inputs and outputs to the ASIC just to make sure that your timing analysis and timing closure is easy to accomplish. It's something that I do. I put one clock and one reset per block. I try not to mix those inside blocks. FIFOs are typically an example where you can't do that. You've got an asynchronous input and an asynchronous output side. That's okay. And lastly, kind of on the same vein of isolating things in wrappers, your mixed signal functions are going to be isolated. It's a good idea to isolate them because your FPGA prototype is not going to have those mixed signal functions in them. You're going to have a functional boundary where you're going to communicate digital signals off to a daughter card where those analog functions exist. So don't bury those inside your design. The goal is to emulate as much of the final design in the FPGA and then switch to the ASIC simulation. And this isolation process will really help that out. One of the things I've found in customer designs over the years that's really struck me, and if you're like me and you want to avoid disaster, reset is everything. And I can't emphasize this enough, take the time to design your reset system up front and test. And that takes on a special significance when you do an FPGA prototype, because in an FPGA, unlike the actual ASIC, everything comes up in a known state after power up. And if you rely on that, your ASIC's not going to function very well. So you must explicitly reset everything in your design. The RAM and ROM and flip-flops in an FPGA are all set to known values. That won't be true. So when you do your design, make sure you do not set any signal going in, any flip-flop output signal to a known 0 or 1. Always use the Verilog X unknown or the VHDL U uninitialized initial value. Partly so you can pick it up in simulation and know that you've got a functional reset problem. And I'd also recommend using a reset controller. Here's an example of one from artillery. If you look at this a little closer, it's taking in an external clock, it's running it through a PLL, and there's some kind of external reset process that comes in, and the controller state machine is responsible for initializing that PLL, getting it to lock, and producing a clock and a synchronized reset directly to inside core block. Let somebody else take care of this initialization process for you. There's some issues to consider when you're doing the FPGA development for your IoT ASIC. Two in particular. The first one is that you're probably going to have a processor. I hope you have a processor. And you're going to need a bootloader for it. And it's typically the first application that gets developed, and it can do a number of things for you as you're trying to bring your design up in the FPGA prototype. The first thing you want to do is have it do a power on self-test of the RAM and make sure that the design is going to function. It's not going to if the RAM is bad. You might want to store it in an external flash for easy upgradability, partly so that when you do your FPGA spin, you don't have to reload the ROM internal to the FPGA. You can load it from something external that might cut down the amount of time in spinning the FPGA design. You'll want to CRC check the firmware that gets loaded to make sure the load process worked. You don't want to be simulating from bad code and trying to track down bugs that are a result of a bad load process. And back to my reset mantra, is your reset working properly? Did all the hardware come up correctly? That bootloader can have a little extra functionality and make sure that that's the case. Also, when you're doing your FPGA prototype, you're going to be making a lot of decisions about what kind of system hardware I need. For instance, if you're doing any DSP work, you might decide, hey, do I need fixed point calculations or floating point? Well, that's a big thing to evaluate early on because the floating point is going to take up a lot more logic in your ASIC. But if you can get away with fixed point, you'd like to know that up front, and the prototype can help you with that. If you're going to be running any kind of operating system, Linux or Android or something like that, you may find that an MMU is necessary in your design. Well, that's also going to take up some space. This is going to help you evaluate the trade-off, whether maybe you even want that high-level operating system because the gate cost is going to be too much. Interrupt controllers. Getting the architecture for various peripherals who all want to interrupt the processor. This is going to allow you to decide, do I really need interrupts or can I use pulled I/O and achieve the same kind of system performance and simplify my system? Lastly, you'll probably want to consider a security coprocessor. Dan talked about IoT devices requiring an elevated level of security, and this is the place where having an FPGA prototype to evaluate that security element or have somebody else evaluate it for you could really come in handy. So what kind of evaluation board are you going to need to do your development and evaluation? Well, there's lots of choices out there for you to consider. Some are very big. You might notice ones for the 10 and 100 million gate ASICs. You don't need those. You need something a little more sized to what the IoT design is going to require. And in that case, you might consider this one evaluation board from Cortus. And one of the things I like about this design is that the Arduino Do I/O footprint is directly on the board. And there probably are hundreds of Arduino boards that you can plug in here that have your mixed signal functionality, A to Ds, DACs, various kinds of MEMS sensors, etc. And they're hooked directly into the FPGA for evaluation. You'll also notice that this particular board has built-in SRAM on it. It's got a 50 megahertz clock oscillator. That's not going to be as fast as your typical ASIC design is going to run, maybe a tenth of the speed, but it's going to get you some actual real performance, and all at a very low price point of around $700. So that's not going to break the bank to get you 3, 4, 5 of these for your software developers to work on and evaluate your design. And lastly, this is your hardware, but what about your IP? And for that, I'm going to introduce Roddy Urquhart from Cortus, who's going to talk to you about the IP requirements for your design. So, Roddy, take it away.
Okay, thanks very much, Tim. So, one of the key elements in an IoT design is going to be a processor. But if you're considering a processor, you don't just need to consider the processor itself, but there is additional hardware and software which is required. There is the peripherals that are required. You may want some hardware security, as already been mentioned. And of course, you need to develop software in order to run on your processor system. You may also need to think about having third-party software, such as a real-time operating system or something like a protocol stack that's going to run on the core. Now, there are many well-known IP providers out there, but you don't necessarily have to go to one of the big ones. For example, Cortus has been described by Electronic Engineering Journal as providing one of the most used but least recognized embedded processors in the world. But of course, we are certainly silicon proven. Over 800 million production integrated circuits have been shipped to date with Cortus cores on board. So if you're wanting to create a thing based on an ASIC that will enable you to stand out, how do you need to consider the processor IP? Well, obviously, you need to have adequate computational performance, but there is also a trade-off between computational performance and power consumption. So most processor IP vendors will offer a range of different cores, allowing you to trade off the complexity of the cores, which gives you the computational performance, with power consumption. Generally speaking, the more powerful the core, the bigger it is, and the more power it consumes. So, if you're not going to make compromises on your design, you want to be sure that you fine-tune this trade-off so that you've got an optimal trade-off between power and performance. In addition, there may be some optional things that you need, such as caches or bus bridges. So if we drill down a little more deeply into this, let's consider a processor subsystem with a processor core, memory, peripherals, and connectivity. So what are the things you need to think about? Well, one you need to think about is the bus connectivity. A very commonly used on-chip bus is the AMBER APB or HB buses, and these may fit your needs. On the other hand, if you have something very simple, you may want to go for something more lightweight, such as the Cortus APS bus. On the other hand, if you have a complex system requiring high embedded performance, you may want to go for a more complex bus, such as AXI4, that can deliver you the functionality that you need. Another important consideration is the arithmetic units that are available. A simple core will just have an ALU in it. However, if your software makes considerable use of multiplication or division, it may be advantageous to have a hardware multiplier or hardware divider in your core in order to give you the performance that you require. The central part of any system will be memories. You'll need a data memory and an instruction memory. So you may need to look into different types of technology that are available, particularly for the instruction memory. If you have slow on-chip memory, or perhaps even off-chip memory, you may need to think about putting in instruction or data caches in order to ensure that your performance doesn't suffer. And talking of performance, you may find that certain operations are computational bottlenecks. Typical things where this may occur are things like cryptographic or DSP algorithms, where certain operations may run too slowly on a general purpose core. In such cases, though, you can create custom accelerators as co-processors, which can allow you to deliver the performance that you require. Peripherals are an essential part of any system. Some of them may be very simple, such as counters, timers, and interrupt controllers, but you may need to have some more complex peripherals, particularly for connectivity. So, for example, you may need an Ethernet MAC or a USB device. And debug is not just an issue for software engineers. You need to be able to debug your hardware. So you may want to have some on-chip blocks, such as breakpoint units, and you will certainly want to have a JTAG interface in order to access your system. So in this slide, we've got an example of a real IoT product from Atmel. It's the WINC 1500. And this is a very low power IoT controller using Wi-Fi for connectivity. It's got a lot of functionality and provides a lot of flexibility in operating modes. It's a general purpose part. Now, if you're considering your own IoT product, an interesting thing is that quite a lot of the functions that are used by Atmel are available in the market as IP blocks. So, for example, you can purchase a processor core. You can purchase a variety of peripheral IP. You can license memory IP, and you can even access things like a subsystem such as an 802.11 MAC. And last but not least, you also have the possibility of accessing analog and mixed signal IP, things like A to D converters, PLLs, and D to A converters. So, if you are going to develop your thing, you could use off-the-shelf components or an off-the-shelf board, such as this Wi-Fi one, or you could create something that is very specific to your application, where you've got exactly the functionality that you require as an ASIC. And an ASIC will sometimes allow your product to stand out from the rest, because you can put in exactly the functionality you want, and also, in many cases, significantly reduce your bill of materials. Another thing to consider is security. As Dan mentioned, there is software security and hardware security. I'm quoting here from a blog from Haggai Bar-El, who is from the security specialist Sensor Security. He makes the point that software implementations are significantly less secure than their hardware equivalents. Reasons for this include the fact that software security tends to use shared memory spaces and executes on top of an operating system. This means there are more opportunities to modify the software than to tamper with the hardware. So something to think about is to include hardware security on your design. Now, you can get off-the-shelf security solutions for hardware, but I'd just for a moment consider an analogy with padlocks. You need to think in terms of who might be attacking your system. Now, if I was wanting to pick padlocks, in this particular case, I would go for the blue padlock, because once I figured that one out, there are a lot of locks that I can attack. It would be much less attractive to go for the red one. And similarly, in IoT security, if you create a custom security solution by customizing your processor IP, you can end up with something unique that is much less attractive to attack. In IoT, one of the major concerns, particularly on edge and gateway devices, is power consumption. Thinking of some of the cells that might be in your design, the power per flip-flop is considerably greater than the power per gate or the power per bit of SRAM. So one commonly used technique to reduce power is clock gating, and this is supported by some synthesis tools. Basically, if you have a block which have flip-flops in it, by clock gating, when that block is not required to be active, you can disable the clocks and reduce the flip-flop activity. This is one of several techniques that you can use to minimize your ASIC design. Another area to reduce power is data transitions on buses. So planning them carefully can reduce power. You might be able to share hardware resources between different functions. If you're careful about state machine encoding, using a technique such as one-hot with less transitions, you can reduce power. And your synthesis tools can provide you with optimizations to reduce gate count or to retime registers in a way that can reduce power. Probably the biggest thing you can do, though, is at the system level. If there are whole blocks of your ASIC that are not required to be running all the time, you can design your ASIC so that these go into sleep or deep sleep modes and basically are spending a lot of the time consuming almost no power at all. If you want more information on power reduction in an ASIC, there's a lot of material available online. Here are 3 examples available from well-known industry websites, and there are plenty more articles as well. So if you have a processor-based subsystem, an important consideration is the development of software. I'd urge you to consider programming in a high-level language like C or C++. Today's compilers are very mature, and it's far more productive to use a high-level language than to program in assembler. Most processor IP vendors will offer software development tools. Very often they're customized GNU development tools with an Eclipse IDE and a vendor-specific instruction set simulator. So what are the things to think about with respect to software development tools? Well, an obvious and simple one is, well, is there a fee associated with them? Or are they free of charge? But probably a more important thing to consider is, how is your thing going to be used? If your customers are going to have to write software to program your thing, you need to be able to provide them with a means of programming the ASIC. So this means you need to find out if your processor IP vendor will allow you to repackage and redistribute the software development tools. If that is the case, this can be an opportunity to make life easier for your customers. If you develop APIs, documentation, and libraries, you can considerably help your customers by offering an easy-to-adopt solution. Another thing to think about is integration of third-party tools. As Tim mentioned, in many cases, a heavy operating system such as Linux would be overkill for an IoT device. What's likely to be far more relevant would be a very lightweight operating system such as Micrium's MicroC OS2 or FreeRTOS. And you may need to think about integrating third-party tools or protocol stacks, or even offering the possibility of a third-party tool such as a Lauterbach debugger. Another very important consideration is code density. Your silicon area is determined not just by the area of your processor, but also by the memories. And very often, the instruction memory is the dominant part of your silicon cost. So the code density, which depends on both the processor core and your compiler, is an extremely important consideration when choosing your IP. An important thing to remember is that different compilers have different options, and these option settings can have a significant effect on the results. So if you're evaluating IP, look at code density. Use real code, not artificial examples, and see how the code density compares in order to optimize the costs of your design and to reduce the risk. So far, we've talked about mainly technical issues, but it's important to consider, obviously, commercial considerations. Now, if you are using IP, you incur costs probably in both the design and the production phases. The most common model used for licensing processor IP is to have an upfront license fee and then royalty fees during the production phase. Of course, there can be variations in this. Some vendors are willing to offer a deal where the costs are focused on an upfront one-off fee. In other cases, vendors may be willing to provide an alternative model where the costs are more back-end loaded. Anyway, you need to consider acquiring processor IP, peripheral IP, driver software, and protocol stacks. Not only that, but as was mentioned before, you will need software development tools. And as Tim explained in some depth, there are great benefits in using FPGA development boards, and these vary in capacity and complexity. And lastly, with most IP, there are support and maintenance fees, which means that the products are commercially supported in a similar way to EDA tools. Now, of course, I've not told the complete story here. It is possible to acquire processor IP, peripheral IP, IP drivers, and protocol stacks free of charge, free of a license fee. However, if you're considering the total cost of ownership, consider your internal engineering resources. If you're dealing with free cores or free software, you have to maintain it and support it yourself. And that is costing you time in terms of your engineering resources. And these resources might be better focused on actually getting your design out. In fact, going for open source is not free of charge. It may in some cases even be more expensive than paying for commercial licenses which are professionally supported. In fact, sometimes going for free licenses may not only be coupled with unexpected costs, but also risks to the timescales of your project. So, summing up, if you're looking at processor IP for your IoT ASIC, consider more than just performance. Remember that you're trading off performance and power. Consider the area in silicon. This will give you a good indication of the cost of your chip and also your power consumption. Consider security. Remember that hardware security is more effective than software security, and the more unique your solution, the more secure it is likely to be. Processor IP is important, but so is peripheral IP, so consider that carefully too. The compiler technology also matters, because an important cost in your silicon is going to be the area of your instruction memory. And as Dan mentioned earlier, in the context of design tools, technical support is important for first-time success. As I mentioned before, if you have a free core, you are having to support it yourself. And even with commercially supported things, bigger does not necessarily mean better. You may, with a large vendor, you will certainly be dealing with call centers, whereas with a small vendor, you may find that you are directly in contact with R&D and in touch with the person who was directly responsible for creating the code that is concerned with your issue. So, carefully consider total cost of ownership over the entire lifetime of your product. Consider whether the vendors offer you different options for IP licensing, and certainly don't forget the impact of any decisions on your own engineering costs. I'll now hand back to Dan for the remainder of the webinar.
Well, thank you, Roddy, and Tim for your presentations. And I think the essential question as a summary is, how are you going to make your thing stand out? And in the Internet of Things, as we get closer and closer to this expected explosion of $50 billion, 50 billion different devices all doing things on the Internet, it's going to be important, and the winners are going to be the ones that can say, I use less battery, I provide more security. I have a facility to maintain and upgrade the embedded code. Your salespeople that selling your things are going to need those kinds of differentiation to win in the battle out in the field. So we encourage you to think about differentiation. It's good to be different. And I hope with the information we've provided you today, you can see it's not scary. There's a lot of myths out there, so be careful about the real data, and you can do it. So say you can, get in touch with the right folks, get a plan together, and you'll be fine. So as we go to the next, we're running a little late in time. I have about 8 questions here that I've collated over the webinar. I'm going to continue on with the webinar and answer these. If people, I apologize, we've run a little bit late. If you need to go, these questions, we can email you the questions and the answers afterwards. And this entire webinar video will be posted on the Cortus website. So do thank you if you're going to stick around. Let me start with the first question. Came in and said, I like the idea of building our own custom hardware. Does Cortus provide tools and services to help their customers do that, or do I have to use a third party? Tell me a little bit about what I could get from a typical IP vendor. I'll let you answer that one, Roddy.
Okay, thanks very much, Dan. As an IP vendor, we offer, obviously, IP, but we also offer services that are closely connected with our IP. So particularly for services that are close to our IP, such as adding security features or creating things like custom peripherals or custom interfaces, this is very much what we can do. We do our own chip designs from time to time, but we're not in the mainstream turnkey IC design business, although we work quite a lot with third-party design houses who offer complete turnkey design services.
Great. Thanks, Roddy. Tim, this one's for you. You had mentioned one of the issues with FPGA boards is you should take your ASIC vendor cells and put wrappers on them and stick them out in the I/O ring. What's an ASIC vendor cell came in? Can you answer that real quick? Just a couple examples, maybe.
ASIC vendor cells go from simple things like maybe an LVDS I/O pin pair to kind of a mid-level thing like a compiled or generated memory cell, like a dual-port memory, all the way up to very highly integrated functions like DDR3 memory controller, PCI Express controller, things like that. So very specialized, small function to large function cells.
Thanks, Tim. Roddy, a question came in on your slide where you're talking about considerations in IP about buses. And you mentioned the APB, HP, and AX4. Can you give us just, the question came in a little bit more detail of what are these buses and where can I get information about them, or what's their legacy?
Okay, these buses are open standards for on-chip interconnect. So they've been very widely used in the industry. They were originally developed by ARM, but they are available as open standards. So the ones that I mentioned, APB stands for Advanced Peripheral Bus. So it tends to be used for interconnecting peripherals. A higher speed one is the AMBER High Performance Bus, AHB, which is a single clock-edged protocol and is quite widely used in medium complexity systems. And then AXI is a more complex standard, generally used for more complex systems, sometimes with multiple processor cores, and it has a lot of extra functionality for the more sophisticated systems.
Great, thank you. So that in essence, these are available to all IP vendors. They're pretty much the standard interconnect for on-chip resources. Tim, I have a question. For you, Tim, about the FPGA board you had talked about. You'd mentioned it runs up to like 50 megahertz. Do people actually run the actual application software, the embedded software? Is it enough horsepower on that kind of a board to actually get something done with the real software running on the real hardware?
Yeah, I would say absolutely yes. It's going to be probably around a tenth of the performance, but it's going to be significantly faster than simulating the gate or RTL level designs. So absolutely, software is certainly a real thing you can do on the FPGA prototype.
So if we were an IoT running at a couple 300 megahertz, it maybe be 1/4 the speed, but definitely responding in real time, so we could actually run the user interface and have a person sitting there actually running the software. So it's a pretty powerful capability. Roddy, this one's for you. Somebody asked, what's an instruction set simulator?
Okay. If you're designing an ASIC with a processor on board, you don't want to be running your software using a low-level description of the design. What an instruction set simulator allows you to do is to simulate the running of your software at a high level. Basically, it mimics the behavior of the processor core by reading instructions and maintaining register values. However, it's a fairly high level of abstraction, which is very suitable for helping you to debug your software, but is not sufficiently detailed to be completely timing accurate.
Gotcha. So it's a trade-off of a higher level of abstraction, so you can run much higher level performance of the simulator. And then as we go through the design process and we get more details about the hardware, which is going to have timing and size and all those information, the simulation will slow down. So thank you. Tim, I have a question. I know this is going to date me a bit, but way back in 1988, when I first started writing Verilog, it took a while to come up to speed. The language was new, synthesis tools. My group was the third group in the United States to ever use the Synopsys compilers, and it took us a while. But today, for a person who's never designed an ASIC, we're just telling them you can. What's the reasonable expectation from your experience working with customers for how long it's going to take them to become, actually designing an ASIC?
Well, I've taught VHDL classes where after a week, people are pretty capable of doing their own designs, and most people consider VHDL to be a little harder than Verilog. So I think for both languages, using the synthesizable subset of each, it's going to be a week to 2 weeks in kind of a formal training environment, maybe around 4 to 6 weeks if they're going online or reading books or kind of self-paced training. But it's all low-level state machines that they're developing, and the synthesizable subsets are pretty manageable for both languages. So, a couple of weeks to a month and a half, and they'll be up to speed.
And I think you mentioned a key word in there. Don't be shy, everybody. Training's available, online tutorials, lots of textbooks.
Oh, yeah.
It's just tremendous amount of resources available, especially in things like synthesizable Verilog and VHDL, because writing one for simulation and writing it for synthesis are two different capabilities. So we encourage you to reach out. Don't be shy. It's your first time. Get people like Tim involved. Go to vendors like Cortus and embrace them, not just as, here's the part I have on the shelf, how many you want. Talk to them about what you want. And one of Roddy's slides, he pointed out, jigsaw puzzles. A lot of vendors today were architecting their IP to be those kinds of blocks that can be pieced together quickly and configured. You don't need a parallel multiplier because you don't need that kind of performance. You want to reduce power and area, swap out a serial multiplier for a parallel. Those kinds of things are available, and generally, the smaller the vendor, the more cooperation you're going to get. So with that, we'll end the webinar. Again, I thank everybody for joining us today. Thank you, Roddy and Tim, for your pearls of wisdom there, and I hope everybody found this webinar useful and informative. We look forward to your feedback. There's an email address on the screen for Roddy. Aspen Logic can be found on their website. And again, we hope you feel like you can design something that's going to stand out. And in this high growth world of the IoT, standing out and being different is what makes the company successful. So thank you, everybody. Have a great day, and go forth and conquer. Everybody design ASICs. That's our mantra. Cheers, everybody.
Thanks.
Thank you.